So let's do an example problem with someone playing with toy cars. When I was a kid, I used to play with Hot Wheels cars, and there was this plastic track, and the car would go down the track and be going fast at the bottom of the track. Okay, and so the question is, how fast is the car going at the bottom of this track? Okay, so we look at the problem and we say, well, wait a minute, we do that. Okay, so we're going down the track here, and we say, we can do the conservation of energy, because otherwise we cannot use our V equals V naught plus AT. That does not hold because the track is curved. And if you look at any one spot on the track, we have mg down, we have normal, so only a component of the weight is making it go. So, but that changes as you go. So this becomes a very complicated sort of thing. It becomes very complicated because the V is going to be the integral, is going to be the integral of the F over M dt, but the F changes, and it actually changes as you go. So this is technically going to be a path integral right here. So it's not just an integral, it's a path integral, because depending on the shape of the curve here is going to determine exactly what the force is at different spots. So this is a very complicated sort of thing. So to really do a true path integral, you have to do calculus 1, calculus 2, calculus 3, and then there's something called advanced calculus after that. And so that's where you talk about these path integrals. We don't want to do that. Remember, best way of doing these integrals that are very complicated integrals is integration by avoidance. Okay, so what do? We say that we can do the conservation of energy at the top and the bottom. So initial kinetic energy plus initial potential energy equals final kinetic plus final potential. Remember, gravity is making it go. Gravity is a conservative force, so we can do this. So we can put we can put at the bottom, say that's going to be my zero of potential. So the final potential is going to be 0. If we let go from rest at the top, the initial kinetic is 0. So mgh equals 1/2 mv squared. The m's cancel, so v equals square root of 2gh. So if I know the initial height here, then I ought to be able to figure out what is the velocity at the end. Now this assumes there's no friction in here, because friction would have taken some of the energy away here, which would have made this a little bit smaller number right here, which would have made the velocity less. But we'll hang on to the idea of friction for just a second. Well, when you're playing with your little Hot Wheels or Matchbox cars or something like that, one of the fun things to do is to have it go down and then over a hill. Okay. And so your car goes down here, goes over a hill. Okay. Now the problem is, if you're not careful, then it goes launching off of the hill right here. Okay, and you know, as a kid, I always thought it was kind of cool to try to launch it off and still laying on the track. But let's see about what is the critical thing. How high can you make this so that it does not go off the track? Suppose it follows right along the track. Obviously, the higher this goes, the more likely it's going to launch off the track. And so I want to know, what's that critical case. So we can pretend this hill is going to be like part of a curve or a circle of radius r. So an object right at the top of it. Okay, free body diagram, we got mg down, we got normal up. Now we know that there's got to be downwards a centripetal force. So the centripetal force is going to be mg down minus the upwards normal. Okay, and then that's going to be equal to mv squared over r. Now, the critical case is when the normal here goes to 0. Obviously, normal can be less than, can be bigger than zero. So that means as you go over, you're going over slow enough that the track is still pushing on you. As you go faster and faster and faster, the normal gets smaller. Remember, we talked about this with going over a hump, and eventually, when you reach the point where you're going too fast, the normal can't, we're assuming it's not going to go to below zero, and so you go launching off because it's not big enough to hold you on there. Now, you look at this and we say, okay, so we now have that mg equals mv squared over r, so that means that v squared equals rg. Okay, now, we're not done yet. If I put my zero right here, now remember we said the potential zero potential can be anywhere. So kinetic initial plus kinetic potential equals kinetic final plus final potential. And so the final potential is zero. If we let go from rest, initial kinetic is zero. So mgh equals 1/2 mv squared. Okay, so the v's cancel. We know that v squared equals rg, so gh equals 1/2 rg. And so the g's cancel. And so h equals 1/2 r. Okay. So that means if my radius of curvature, so for example, if the radius of curvature were 12 inches, then that means that the biggest h can be is going to be 6 inches in order to go over the top. Okay. And so that's one of the things that you learn here. Now, a couple of things about this. As a kid, you didn't want it to go off, so what do? Well, you could make the height not too tall. This is the max it can be, is 1/2 r bigger. Or if you want it to come from higher, you've got to change r. You've got to make this curve flatter. Okay, the sharper that is, the slower you can go over it. And so there's two different ways of fixing the problem. Now, this assumes there's no friction. What if there were friction? What if the work done to friction were minus point, or what if the work done to friction were 25% of the initial? Okay. Well, it should be negative because it's taking energy out. So that means that K initial plus U initial plus the work done by friction is going to be equal to K final plus U final. Okay, that didn't change. This didn't change. So this is mgh minus 0.25 of the initial, and that's equal to 1/2 mv squared. The m's cancel. That's going to be equal to 1/2 rg. Okay, and so we find over here the g's are now going to cancel, and then we get 0.75 h equals 1/2 r, or in other words, h is going to be equal to r divided by 1.5. Okay, so that means that, well, that means that if r is 12 inches, then h, okay, would be 8 inches. Okay, so friction robbed you a little bit of this energy, and so that means that because of friction, then this would have to be a little bit higher. Okay, and so again, if you had one of the really good cars that had very low friction, then they go really, really fast, and they'd be more likely to go off the top of the incline than maybe one of the cars that had more friction and wasn't going as fast. Now, there are other factors that play into this. We're not including the energy that goes into the spinning of the wheels. We get to that later in the semester. One other thing. We had made the assumption that I'm putting right here at the top here, I called that 0. What if I'd called this 0 down here? Okay. Then and I want to know what's the speed up here. Okay, so this is like some h, that's what we're after, how much higher than the top. This is some extra y right there. And so that means that, now same thing, we have initial plus initial kinetic, we have the initial kinetic plus potential equals the final kinetic plus potential. Well, initial here is 0, so we get mg h plus y equals 1/2 mv squared plus mgy. The m's cancel here. Okay, we do some algebra and we find that GH equals 1/2 V squared. Wait a minute, this is the exact same thing that we had before. Okay, it turns out that by moving the origin, we did not change this. We just added an extra step of algebra is all that happened. So again, this is not a big deal. So you can put the origin anywhere you want. You can put the origin down here. You could have put the origin right where I did at the top of the thing. You could have put the origin at the very top and called that the final right here minus mgh. Okay, and said that the initial potential energy was 0. And then if you do that, then the equation would have looked like 0 equals 1/2 mv squared minus mgh. Well, guess what? That's the same equation that we had before, just different algebra. So it always works out the same way. That's the really cool thing here. Well, one more example. Suppose that we had a loop-de-loop right here, okay, and some radius of curvature right here, okay. And again, I want to know how high does this have to be so that it does not fall off the loop-de-loop. I want it to go all the way around, okay. So in this case, then, well, same thing at the top up here, we've got free body diagram, we got mg pulling down, but we also got the normal pushing down. So mg plus the normal equals the centripetal force, mv squared over r. The critical case is when the normal is 0. So once again, we have that v squared equals rg after a couple steps of algebra. Once again, if I put my 0 right here and say this is some height h, then mgh equals 1/2 mv squared, and we end up with h equal r over 2 again. So same thing. Now, there is a slight difference between that case and this case. So in both cases, we found the h equals r over 2, ignoring friction. Okay, so h equals r over 2. The difference is that's the max h. So that means that h has to be less than or equal to r over 2 in order to avoid going off the top. In this case, that's the minimum h. So h has to be greater than or equal to r over 2 in order to avoid falling off. Okay, and so that's the big difference in these two equations. We found the critical case, h equals r over 2, is the same for both of them, but in this case, that critical case was the maximum h, and in the other case, that critical case was the minimum h.